let's get started for today. First thing, most people probably noticed that I've got your grades posted from the first term test. So those are under your grade section on Brightspace. I brought the tests with me. I think I should be able to give them back after class. It won't take more than a couple of minutes. So maybe we'll even quit a couple of minutes early so I can pass them back. Overall, I think maybe some people were disappointed in their grade. I've gotten a little bit of feedback, people letting me know they thought they were going to do a little better. And overall, I wouldn't say that the class did really super. And we're kind of noticing, like a bunch of people from a bunch of other departments, we kind of compared notes with how students did on the first term test. And overall, it's not so hot. And my best guess is that kind of all the horrible high school stuff you had to go through is kind of catching up with us now. So a bunch of the lost instruction and a bunch of the changed testing policies, and now we're kind of catching up where all that happens. So I think now that you've got one test under your belt and you sort of see what to expect, what it looks like, when you get your test back, you'll be able to look at what you submitted and what I expected for full points. So like you can get a clear idea of the expectation beyond what we do in class. You'll have a clearer idea of what to expect the test is going to look like. And I think people can probably, and I expect students probably will, do pretty well on the next test and the final. Because the class didn't do really super, and I really hate for people to kind of give up hope when I know a lot of people wanted to do really well. If you do better on the final exam, I'll move the weight of this test onto the final exam. So say you got 50 on this test, but you got 80 on the final. I'll just strike out this mark, I'll put your 80 in, and you can move forward. So sort of good grades are still in the ballpark for everybody. I think that's everything I wanted to say about the test. Any questions? No? Okay. So last day we did a lot about electric potential. We talked about electric potential with constant electric fields. We looked at how potential related to field. We looked at the potential of a conductor in general and of a spherical conductor. We thought about equipotentials, and we thought about the electric fields around pointy things. So we're going to pick up today back with potential and talk about ways to visualize potential. So that's where we're going for today. Okay, anybody recognize this? It's like one of the prettiest hills of all time, right now, Fuji. So we're going to talk about how to visualize electric potential and how to relate electric field and electric potential. So the first thing I'm going to do is just throw a throwback to when you did a geography class and talked about contour maps. People talk about that in geography class? Some people. Hikers might know about contour maps. So what a contour map is, you draw a line that shows an equal height. So everywhere on this red line is 2,000 meters above sea level, and from a top-down view, it's right here. Then 2250 is the next line, 2500 is the next line, and so on. So these maps tell you how high the hill is. Something you can see from these maps, if we have places where the lines are really close together, it means you get a big change in height over a short horizontal distance. That's a really steep part of the hill. If the lines are all spread out like here, it takes a lot of horizontal distance to get a change in height. That's a shallower part of the hill. We're going to do this sort of thing with potential. We'll draw lines with equal potential, and the steepness will relate to the electric field. So geographers will like this. If you don't like geography, you can probably forget it at this point. So let's go to our example of a capacitor. And let's look at that sort of a map for a capacitor. So we talked about this a little bit when we did our equation, that the change in potential was negative the integral of E dot ds. Something we said is if you move along a path perpendicular to the electric field, the potential is constant. The change of potential is 0. So now we've got a new definition, or a new terminology, equipotential lines. So an equipotential line is a line along which the electric potential is constant. If we put that together with our equation, we know that that's going to be a line that's perpendicular to the electric field, because V is constant whenever we move perpendicular to a field. Equipotential lines are evenly spaced in potential. So when we draw a set of equipotential lines, they'll always be separated by 100 volts or 20 volts or 1,000 volts, always separated by the same amount in potential. Okay, so we're going to start drawing equipotential lines. So let's think about if we have a parallel plate capacitor. Plates are separated by 1 millimeter. Let's say the field is 100,000 newtons per coulomb. When we draw a coordinate system, we use the s-axis, where s is the position relative to the negative plate. S equals 0 is the negative plate. If we wanted to find the electric potential at any place between the capacitor plates, we would use the expression we came up with last class. The electric potential V is the electric field times the distance from the negative plate. So let's find the electric potential at some distances relative to the negative plate. So the first distance, let's find the potential at 0 distance from the plate, at the negative plate. If S equals 0, then the potential is E times 0, the potential is equal to 0, and that'll be measured in volts. So anytime we are at the negative plate, we get a potential of 0. Doesn't matter where we are vertically, we just have to be 0 meters from that plate. So everywhere on this line, the electric potential is 0. The next line we'll look at, what if we're at 0.25 millimeters? To get our potential, we'll do 100,000 newtons per coulomb times 0.25 times 10 to the minus 3 meters. So the field times the distance. And what we get for that is 25 volts. So every time we're 0.25 millimeters from that negative plate, the electric potential is 25 volts. Half a millimeter from the plate, we do E times distance, we get 50 volts. So we draw a line every time we were 0.5 millimeters from the plate. 0.75 millimeters, we get 75 volts. And 1 millimeter is at the positive plate, that's at 100 volts. So these dashed lines that we drew, those are lines along which the potential is constant. These are the equipotential lines for the capacitor. And probably most often in the notes, I'll just write EPL for equipotential line. Okay, so that's how we draw them. We think about where the potential is going to be equal. So the relationship between the electric field lines, those are our green arrows there. We can make them a little bit darker. So the relationship between our equipotential lines and our electric field lines. Number one, the equipotential lines are perpendicular to the electric field lines. We see that in our picture. We know that from our equation because delta V is 0 if our path is perpendicular to the electric field. So this is something that's always going to be true. This is a fact you'll use to help you draw maps of these equipotential lines. Another thing we know is that electric field lines point towards low potential. We see that in our picture. This one is 100 volts. That's a high potential. This one is 0 volts. That's a comparatively lower potential. And our electric field lines point from the high to the low. So that's a fact we know. What else? Equipotential lines, by definition, are always evenly spaced in potential. So in this diagram, we drew the equipotential lines every 25 volts. We also could have drawn them every 10 volts. It just has to be an even amount. And then the last thing I'll toss in is just a comment for where we're going to go in some of these problems. We're also commonly going to do some problems where we write the electric potential energy is the charge times the electric potential. We'll also use that work is minus the change in electric potential energy, and we'll also use conservation of energy. So that's where we're going to go with some problems and examples as we go through. Okay, questions to here? No, it's pretty straightforward stuff. So that's if we have a constant electric field. You might notice here in this picture that our equipotential lines are also evenly spaced in distance. So they're all 1/4 millimeter apart. And this is a constant electric field. Our next question might be, what if the electric field is not constant? That's the next one we'll look at. We'll look at what happens around a point charge. So we'd like to visualize the electric potential around a 10 nanocoulomb charge. We might just call that charge Q. There are a few different ways to do it. If we wanted to think about the potential as a function of distance from the center of the charge, we could just do a graph, okay? And we definitely often do lots of graphs. So we could make a graph. To draw our graph, we would remember that V equals K times Q divided by R. So if we put our potential on the y-axis, our distance from the center on the horizontal axis, if R is small, the potential is big. If R is big, the potential is small. And it goes as 1/R. Okay, so something like that. So that's one way to think about the electric potential. We could just draw a graph. And then the other way, where we're going to focus now for a little while, is to use the equipotential lines. And I've just got our definition written down again. Let's think about those similar to what we did on the last slide, but not exactly the same. So our equipotential lines are lines with constant potential, so they're places where the potential is always the same. If we want to figure those out, well, we know that V is K times Q over R. We might ask, for what distance R do we have a constant potential? Okay, so if we want to draw the equipotential lines, we want to know where they are. So R is equal to K times Q divided by V. So if we want to find those lines, let's pick some potentials, let's have them evenly spaced, and let's find some of those distances. So I'm going to pick some potentials. I'm going to start at 2,500 volts. I'm going to go up by 2,500 till I get to 12,500. And I'm going to figure out my distances for each of those. When I know the distances, I'm going to draw the lines. So for my first one, if V is 2,500 volts, then R is K times Q, 10 times 10 to the minus 9, divided by V, 2,500. That first distance, R, turns out to be 3.6 times 10 to the minus 2 meters. Okay, so there's our first calculation. 3.6 times 10 to the minus 2 would be the same as 36 millimeters. Okay, so there's our first distance. So we'd like to draw a line that's 36 millimeters from our charge. That would be a circle. So every time I'm 36 millimeters away, that would be a circle, or in 3 dimensions, it would be a sphere. So this is a sphere centered on my charge Q. It's got a radius of 36 millimeters. Everywhere on this line, it has a potential of 2,500 volts. Okay, so there's one equipotential line. For my next equipotential line, I'll put in V equals 5,000 volts, and what I'm going to get for my distance is 18 millimeters. So I'll draw that line next. So 18 millimeters away is right here. Everywhere on this line, the potential is 5,000 volts. For my next one, I'll go up by 5,000 again, or 2,500 again. If my potential is 7,500 volts, that comes at a distance of 9 millimeters. And I'll draw that line. That one's 7,500. Okay, next line, if I go up to 10,000 volts, my line, oh sorry, that should have been 12 millimeters. My next line at 10,000 volts is at 9 millimeters. And then the last one I'll draw, because they're starting to get difficult to draw, would be 2,500 higher. That happens at 7.2 millimeters, which is in right here. This one is 12,500 volts. So there's my set of equipotential lines around a positive point charge. Let's think about sort of the comments we made on the previous slide, and how does that match with what we see here. So on the previous slide, we said that the equipotential lines were perpendicular to the electric field lines. Let's draw the electric field lines here. We know that they point radially out of a positive. So here are the electric field lines. The electric field lines are radially out. The equipotential lines are spheres. So by definition, those two things are perpendicular. So our first comment holds true. The equipotential lines are perpendicular to the electric field lines. We said that the electric field points from high potential to low potential. So in here at the center, we have high potential. So here's high potential. Out here, at the furthest one out, this is an area of low potential. So yes, we still get that same behavior that the electric field lines point from high to low potential. That's a behavior that we see that's due to the negative sign in our equation. Okay, some other comments that we're going to notice here. When we drew our electric field line maps, we said that our electric fields were the strongest, where the electric field lines were closest together. That behavior is also true for the equipotential lines. Where the equipotential lines are close together, the field is big. Where the equipotential lines are far apart, the field is small. So the size, the spacing of the equipotential lines tells us about the size of the field. So E is strongest. Where the equipotential lines are closest. So that's a behavior we didn't see on the last slide because our electric field was constant. Now the other thing was the relationship between field and potential. We know that field is the negative of the change of potential with respect to space. Here our electric field is radial. So the radial component of the electric field is minus the change in potential with respect to the radial distance. Okay, so that's a reminder of what happens here. Any questions here? So I'm going to switch over to the PhET simulation for electric fields because we can also use that to look at potentials. And I think that one might help you a bit when you're doing some of your studying or your homework. So here's the simulation. If you want to try this out, you Google PhET, P-H-E-T, electric fields. The first hit will be this simulation. We've used this before to draw electric field lines. We can use it now to draw equipotential lines. So over here we have a sensor. I'm going to move it in until I find a place where the potential is 12.5 volts. Sort of hard to be perfect, then I'll draw the line. Then I'm going to move it out to 10 volts, 7.5, 5, and 2.5. So for something straightforward like the round charge, you don't really need the simulation to draw them, but it can be really helpful for other kinds of charges. Other things you can do here is you can measure the electric field at different places. So this is an electric field sensor. We see that the field is really big in here. So in close, the field is really big. So here it's like 17 volts per meter. As we get out here, the electric field gets smaller and smaller, and the potential gets smaller as we get further away. So these simulations can be really useful. We'll use that in our next example as well. So this is a sort of a combination problem. This builds on what we did in our electric fields chapter. It also talks about the potential around a point charge. It includes drawing electric field lines, and we add in drawing equipotential lines. So this would be the sort of a problem you'd see on a test because it covers lots of different chapters. It pulls it all together. So draw the electric field lines around the following system of charges. So we're going to draw the electric field lines using the things that we remember about drawing electric field lines. They point out of a positive or into a negative. Electric field lines can't cross. And what else? If we have an equal size charge, then they have to have the same number of lines. So let's use those ideas and draw these electric field lines. So I'm going to start with the two easiest ones. Out here on this side, the electric field points all the way away. Out here it points away. For the lines that sort of go close to each other, if a line comes out of this charge, it can't go into this one because this is a positive, it goes into a negative. So it has to be veering away from that positive. It will go something like this. Likewise down here. And then we can draw a few more. You could draw more lines if you wanted to, but this gives you the gist of it. Okay, questions here? That's a recap from our electric field chapter. Next, we want to draw the equipotential lines. So what we know about equipotential lines is that they have to be perpendicular to the electric field lines. They're going to be bigger where the lines are close to, or the potential will be bigger where the lines are closest, and the potential will be smaller where they're far apart. Okay, equipotential lines, when you have a map like this, it's hard to get them really good. If this is a test question, then the most important thing you can convey to me is that you know the idea of how to draw them. So I'm going to try drawing them. I'm going to start by knowing that they have to be perpendicular. So my first line I draw is a dashed line, and it's perpendicular to that. To come around, I'm going to be perpendicular here, perpendicular here, and here, and here. So to stay perpendicular, I kind of have to swell out a bit on this side because of the way that these lines are shaped. I know that it's going to look the same for both charges. Okay, so it looks like this on this side. By rights, I should have drawn those with exactly the same radii, but I am not perfect, so my diagram's not going to be perfect. My next one I'll draw, sort of following that one a bit. And I'm going to draw one more, because you should try and draw at least 3 of them to show that you know that they spread out as the field gets weaker. Okay, any questions here? So I would say that if this was a test question, most people should be able to get this bit. If you really started thinking hard about it, you might be able to get some of the stuff in the middle, but that's a bit trickier. So with a new configuration, I'd sort of expect you to get this much. Yeah.
Since equipotential kind of, in some instances, expands past where the curve is going, can the equipotential lines cross or not?
Can equipotential lines cross? That's such a good question, and I'm going to show that on the simulation. Equipotential lines could, in some cases, cross. The reason electric field lines can't cross is because they're vectors. They can't have 2 directions in once. Equipotential lines are not the same thing, right? They're not vectors, so there is some differences there. So let me get these labeled. So these are the equipotential lines. These are the electric field lines. Let's have a look at this on our simulation. So the first equipotential line I'm going to draw is going to be right dead in the center. Okay, so you see that they do touch. Right here they touch in the middle. That's kind of interesting. I'll just draw a couple more. 20, 30, and 40. So if you were drawing these maps as you were studying, try and get it by knowing what they're supposed to look like, and then you can just try confirming it with the simulation. So we see that sort of nifty bit here in the center, where they kind of come to a common point in the middle. So that's kind of interesting. It might be hard to get that if you were drawing this fresh from scratch, but these kind of circular bits, you should be able to figure those out. Yeah.
Is that crossed because it's the lowest potential energy at that instance?
It's because the potentials are equal right here. Yeah, so that's why it crosses, because it has the same potential from both. Yeah. Okay, so back to our example, because we got a couple more bits to do. So we drew the electric field lines, we drew the equipotential lines. Find the electric field and the electric potential at the point shown. So this is a review of what we did with our electric field chapter and our electric potential. So at point P, there's an electric field due to this charge and an electric field due to this charge. I'm going to call those charges 1 and 2. There's an electric field at point 1 due to charge 1. Charge 1 is positive, so the electric field at point 1 at P due to charge 1 points away. There's E1. My electric field at point P due to charge 2, also points away. So here's my charge 2 because it's positive. We're closer to this one, so that electric field should be bigger. E2. So my total electric field at point P would be the vector sum of those two. I think we can do that bit a little bit quickly. So my net electric field at P is E1 plus E2. E1 is K times Q1 over R1. R1 is my distance between my point and my charge 1. R1 equals 0.2 centimeters. That direction is to the right. I'm going to call that the positive x direction. Plus E2, K, Q2 over R2. Those R's should be squared. That's also to the right, or I hat. R2 is from my charge 2 to my point, 0.1 centimeters. So there are my distances. Q1 and Q2 are given in the problem. Q1 equals Q2, 2.36 times 10 to the minus 6 coulombs. Put all this in your calculator, and you should get that the electric field at point P is 2.65 times 10 to the 10 newtons per coulomb or volts per meter. Okay, so that one's a recap of finding fields due to point charges. Yep.
Isn't it the nanocoulombs?
Given in this problem was microcoulombs.
Oh.
Yeah. There, I zoomed in so far we lost that one. Okay, any questions there? Okay, we're also asked to find the electric potential at point P. So that's the electric potential due to our 2 point charges. We can use our equation for potential there. So our potential at point P is the potential due to 1 plus the potential due to 2. Due to 1 is KQ1 over R1. Due to 2 is KQ2 over R2. Put that in the calculator and we should get 3.18 times 10 to the 7 volts. Yep.
It's supposed to be volts per meter. Or the
Electric field is volts per meter. Electric potential is volts. Okay, so that's one example. I've got another one that I'm going to post as a homework example. It's similar, but instead of 2 pluses, I'll give you a plus and a minus. So otherwise, it's pretty similar. So the next one, I took this off a midterm or final exam that I gave last year or the year before. So I picked this one on purpose because it was an exam type question. Again, this is kind of a combo question because it incorporates a bunch of different things. So in this question, what I've got here are 2 charges. The red lines are the electric field lines, and the green lines are the equipotential lines. So these are the electric field lines. The green ones are the equipotential lines. We know that the equipotential lines are separated by 1,000 volts. We want to find the field at point A, the work done by the field on an electron as it moves from B to C. Here I've got a small typo that I would like for you to fix, please. I said if a proton is released at C, what's its speed when it gets to B? B and C should be switched there. We release the proton at B. What will be its speed when it gets to C? Okay, so small change there. The last thing I'm going to add is that we're going to assume this diagram is to scale. So everything is the real physical size. So we'll put that in our words too. Okay, the first part, label the charges as positive or negative. This is something you should be able to get from the electric field lines. We know they go out of positive and into negative. So we look at our charges, the field lines come out of this one, that must be a positive. They go into this one, that must be a negative. Another question could be rank the sizes of the charge. Is one bigger than the other, or are they the same? To figure that out, you count the number of lines, because you know the number of lines is proportional to the amount of charge. These both have the same number of lines, so they must be equal and opposite charges. Okay, the equipotential lines are separated by 1,000 volts, and we want to find the field at point A. So let's do something with this wording. The equipotential lines are separated by 1,000 volts. Can we figure out what the different potentials are? So if we go exactly in between two equal and opposite charges at exactly the midpoint, what would the potential be right there? Equal. I agree that it's going to be what? Equal to what? What's
Zero.
the potential? 0. So right here, the potential at A due to this charge is K times Q divided by this distance where your charge is positive. The potential here due to this charge is K times Q divided by this distance. Those two distances are the same. The two charges are equal and opposite, so the two potentials are equal and opposite. The net potential at point A has got to be 0.
Does that mean the potential at the negative charge would be negative?
Yes, and the potentials over here are negative, the potentials over here are positive. So our potential at A has to be 0. So V at A equals V1 plus V2. So I'm going to call that charge 1, charge 2. K Q1 divided by R plus K times Q2 divided by R. Those distances R's have to be the same. It's from the charge to the point. Equals 0 because Q1 and Q2 equal and opposite. Okay, so now we can start labeling the potentials. Everywhere where we have this line, that's potential is 0. They're separated by 1,000 volts. As we get close to the positive charge, the potentials have to be positive. So this one is 1,000 volts. This one is 2,000 volts. This one is 3,000 volts. This one is 4,000 volts, and so on. As we go to the negative charges, our potentials go negative, minus 1,000 volts, minus 2,000 volts, minus 3,000 volts, minus 4,000, minus 5,000, and so on. Okay, so now we can label all of our potentials. Are we good to hear? Yep.
Could you skip the equation and just say, since we can infer that Q1 is equal to Q2 but opposite, that the potential at that point would be 0?
Yeah, you could explain this conceptually. You wouldn't have to explain it with an equation. You know, they're equal distance from equal and opposite charges, so the net potential's got to be 0. That's fine. Okay, so find the electric field at point A. If we wanted to do like we did on the previous example, draw the electric field due to this one, draw the electric field due to this one. The fields are KQ over R squared. You'd notice you got stuck awfully quickly because we don't know Q. So is there a different way to find the electric field from knowing the potentials? And I'm going to say the answer to that question is definitely. So let's try and find the electric field at point A. That diagram is so full that I'm just going to try and sketch out, copy that diagram a little bit. So I'm going to draw this equipotential line, and this line. Here's my point A. This is 0 volts, this is 1,000, and this is minus 1,000. Okay, so I'm just copying that part of the diagram so I don't have to write on top of this one. if I want to think about how to find my electric field when I know my potential, I know that electric field, the magnitude of my field is going to be the magnitude of my change in potential divided by the separation between the 2 points. Okay, so there's a relationship between field and potential. I know these two potentials, so delta V is a piece of cake. If I know my distance, then I'll be able to calculate my electric field. Okay, so that's what I'm going to do. That's why I started the problem by saying, let's assume that this is to scale. So my distance between these 2 points, if I put my ruler up, it's really hard to see. Okay, so if we zoom right in, we can see that the distance between those 2 points, to my best estimate, is about 13 millimeters. Okay, so it goes from here to here. That's about 13 millimeters. So I've got the space between the 2 points. I know delta S. I can figure out my delta V so I can find my electric field. So delta S is the distance from here to here. Delta V is the difference in potentials. So if I called my points 1 and 2, point 1, point 2, delta V is the difference between potential 2 minus potential 1, the difference between minus 1,000 volts, subtract 1,000 volts. So the size and the difference in potential is 2,000 volts. So now I can find the size of my electric field. And I get 1.54 times 10 to the 5 volts per meter. Electric field is a vector, so we do have to put the direction on here. Let's come back to our picture to make sure we know what the direction is. So if we look at the picture, our electric field line at point A is going straight from the positive to the negative. It points to the right. Okay, so looking at this diagram tells us the direction of the electric field vector. Okay, so sometimes you can use delta V over delta D to find your electric field. Sometimes you can use the point charges. You got to take stock with what you're given and what you know to see which one is the more appropriate way.
Should we bring a calculator then to or not a calculator, a ruler?
Definitely a calculator. You may want to have a ruler. If I give you a problem where you need to use a scale, typically I'll put the scale on the bottom of the diagram. Like I'll put the scale here. So you could measure your distance on the diagram and then hold it up to the scale. Like, I'll give you a tool to be able to do that. And there's a box of rulers in the lab. Yeah. So bring one if you wish, but I got your back if you don't have one and you need one. Any questions? Okay, so that's finding field when we know potentials. We were also asked, what is the work done by the field on an electron as it moves from B to C? So we're going to take an electron over here next to this positive charge. It's going to move over here next to this negative charge, and how much work is done on it. So for this part, we know that work equals minus delta U. Delta U is Q times delta V, so I have negative charge of an electron times delta V. Charge on an electron is negative of the fundamental charge. Delta V is my final potential, so it moves from B to C, so that's the potential at C. Subtract my initial potential, it starts at B, EV. So that's plus E times VC minus VB. Okay, so there's how I'm going to calculate the work done. The fundamental charge is 1.6 times 10 to the minus 19 coulombs. V at C You've got to get that from the diagram. So we labeled all of our equipotential lines. In there at point C, the potential was minus 5,000 volts. Subtract our potential at B. We labeled that one on the diagram too. That was 3,000 volts. And that gives us a total work done of negative 1.28 times 10 to the minus 15 joules. If we think about what does it mean that the work done by the electric field is negative, it means that the force and the displacement were opposite. Let's look at our picture to see, does that kind of make sense? If I'm taking an electron and moving it towards a negative charge, the electric force would certainly be repulsive. That would be opposite the path of motion. So yeah, it makes sense that that work done would be negative. Questions? Okay, one last bit of this question. If a proton is released at B and allowed to move freely, what will be its speed when it gets over here to point C? So our proton makes sense, we'll move from a positive towards a negative. We want to find its speed. Again, you could not use kinematics here because the force is changing as we move around. If force changes, acceleration changes, so this has to be an energy problem. So for our proton, we'll write down conservation of energy. Final total mechanical energy is initial total mechanical energy plus work done by non-conservative forces. There's no friction or anything like that. We're going to say that our final point is at point C because that's where it ends up. Our initial point is at point B because that's where it starts. So our final total mechanical energy is the kinetic energy at C plus the electric potential energy at C equals the initial energy, which is the kinetic at B, plus the electric potential at B. So there's our conservation of energy. Let's think about what we have to put in for each of those terms. The kinetic energy at point C is 1/2 times the mass of a proton times the speed at point C squared. That's the bit we're trying to figure out. The electric potential energy at C is the charge on a proton times the electric potential at C, so the fundamental charge times the potential at C. The kinetic energy at B is 1/2 times mass of a proton times the speed at B squared. That's 0. It says we release it, so we let it go. It starts from rest. The electric potential energy at B is the charge of a proton times the potential at B, so that's E times V. So there's our bits to put into that equation. 1/2 times m times vc squared plus E times vc equals 0 plus E times vb. So 1/2 mass times vc squared is EVB minus EVC. VC is 2 times EVB minus EVC divided by the mass of a proton, take the square root. So that speed turns out to be 1.24 times 10 to the 6 meters per second. Okay, so when we started with our first slide today, I said we'll often do things like work is minus delta U. We use conservation of energy. So here's a kind of a problem where you can see that show up. Any questions? Okay, so our time is up. We'll quit there. And if you want to stick around for a few